Okay, so good afternoon, everyone. I'm pleased to introduce the first event in the DISI Seminar Series. This is meant to be the first in a hopefully long list of events organized by our department. And the seminar of today by Fosca Giannotti and the one planned for the 17th of February by Francisco La Gioia will deal with some transversal topics in artificial intelligence. And in particular, here we'll talk about explainability and fairness. So let me introduce the speaker of today, Fosca Giannotti, Director of Research of Computer Science at the Information Science and Technology Institute, FAEDO, of the National Research Council of Pisa. Her research focus is on social mining from big data, smart cities, human dynamics, social and economic networks, ethic and trust, diffusion of innovations. Today's talk provides a reasoned introduction to the work of explainable AI to date, and surveys the literature with a focus on machine learning and symbolic AI-related approaches. So welcome our speaker, Fosca Giannotti, and the floor is yours. You're muted, sorry.
Okay, thanks for the introduction and thanks for the invitation. I'm honored to be here. I didn't know that I was the first of this series, so I wish you success for the rest. Thanks for having me here. So the talk of today is about explainable machine learning for trustworthy AI, and it is a now let me see how it move. Sorry. And it is a joint work which is pursued within the ERC project, Explainable AI, Science and Technology for the Explanation for AI Decision Making, joint with the University of Pisa and plenty of collaborations and new young researchers which are working hardly on this project. Sorry, but okay. So I will start with talking about artificial intelligence. It's difficult not to mention Alan Turing, and is a game that the imitation game that was instead of defining what is computing machinery intelligence, he decided to revert the problem, say that, okay, we can say that a machine is intelligent once the actions, the tasks which are performed by the machines are indistinguishable by the fact that the same task is solved by a humans, by a humans itself. There is another human which is observing the results, and he or she cannot distinguish. So now the problem is that, are we there? Are we almost there at the point that Alan Turing was imagining? Think, for example, the terrific advantages which have been done in natural language processing in translations. If you take DeepL, for example, and then you ask for translation in any of the languages that are there, even of a piece of a poem, you will see that the translation preserve the sensibility of a poem. So really it would be difficult to distinguish if it is related. Same for the pictures, the image. So we are nowadays exposed continuously by the advantages of AI in image processing, and the capacity. I mean, in our mobile phone, the pictures that we have every day have a new service which expose us and combine images also with text. And same for our for the many recommender system that we are exposed to. The quality of the information, the accuracy of the information is every day much more useful and efficient. But fantastic advances, but mind the traps. Not everything is it's perfect. There are still traps. Traps are the fact that so those systems, when they are used in high stakes scenarios, where we are taking, using them for taking decisions, very important decisions, there cannot be mistakes, or there cannot be things which are not completely understand. There are plenty of examples in these days in criminal justice, finance, healthcare, where those systems are used. They bring more efficient performance when they collaborate with humans, but still there are some risk. I will give three small examples which are nowadays very, very famous. They are almost a manifesto of the possible mistakes. One is this system which is trained for recognizing capable of distinguishing among dogs and ASCII dogs and wolves. And the system has been trained on pictures which have been annotated by humans, so husky and wolves. And then the system with on the training set, very, very good accuracy. It failed, the system failed when classifying badly an husky and was classified as a wolf. This picture, so what was the mistakes? If you try to understand what has been the motivation for this classification, you see that the most important features which contributed to these classifications were the white pixel. In other words, the snow behind the pictures. So what happens that all the pictures of wolves in the training data set had in the background the snow. So it's not actually the system was particularly smart. It chooses the most efficient features for reaching the classification. That was the snow behind, but there was a mistake. So the problem was that in the data there were biases. Same, another famous, even more critical example is the system Compass, used in US for ranking from judges to rank the risk of reiteration for people that were asking for a special in jail, were asking for a special form of freedom, limited form of freedom. But there was the judges were helped by this ranking that was learned using the historical data of other judges' decisions, which is useful. But the problem is that the final decision was biased by the fact that the black people was always systematically ranked with the high risk, even with the same profile. Comparing the same profile with an Italian, with white guys, they had with same profile. I mean, profile in terms of criminal profile, they had systematically a higher risk. So that was, of course, due to the fact that the population in jail in US it's much more black people. So I mean, there are statistical motivations for doing this. The problem is that if when you return to a decision maker only this information, simply a number which rank the person, and there isn't the appropriate explanation on the logic which was behind reaching that explanation. So the judges has two possibilities: or do not trust the system and throw away the suggestion and start to reason by himself or herself, or completely delegate to the algorithm the decision, because this is I mean, maybe safer. So it's difficult to contrast an algorithm, so and they delegate. So there are, and both those two solutions are not useful, are not if you are going this direction, we are not achieving really the dream of providing to with the AI system something which is useful for taking better decisions. So if we completely clarify the logic which is behind, imagine that a judges understand that one of the motivations for having this high risk was the race. Of course, the judges would haven't taken that in consideration. It is not legal. Okay, so this is why we need to have a explanation is an important topic. And there are also other traps like robustness. So we know that also robustness is another risk of current technology of machine learning, for example, of deep learning. So it's very easy to fool such system. So we need to have some robustness criteria behind this, and again, explanations. In this case, an explanation which is oriented to the developer, having tools for understanding what is happening during the training. It is an important tool also for the developer as well. So first point. So if we want to do an artificial intelligence that is useful for humans. So we don't want machines which are intelligent, but we want to make humans more intelligent. So provide tools which help them, and those tools have to be also ethical, in some sense. That we have to be sure that they do not harm. They preserve the human agency. When I was saying before, so putting the human, the decision makers in condition not to delegate, not even, but making a better decision thanks to the fact that trust is there, and then justice, of course, in the rule of law, and what else. And explicability is a basic brick of this of having this. Of course, GDPR is also making this an important part of the new general data protection regulations, and that it established the right of obtaining meaningful explanations again. So what we are doing in this ERC project started 1 year and a half ago, it's exactly focusing on explanation. It's an important brick for preserving and expanding human autonomy, human agency. So helping human to make better decisions. So this is the final goal. Unfortunately, not only us, but nowadays there is plenty, and that's very challenging. Plenty of researchers which are focusing on the same. So objective is to empower individual engaged and decide the effect of humans human decision making, implement the right of GDPR, and help people to make better decisions. So what I have in mind, it's the Dr. House model. So Dr. House, it's a very intelligent person that asks help. It uses other very intelligent agents, very intelligent people with help him and providing new hypotheses, challenging him, new information, and but at the end, it's Dr. House, the one which takes the responsibility of finding a solution. All these intelligent contributions to its decision making help him to achieve a better decision. That's the model that we want to have in this project. There are several lines. One is algorithms and models for explainable machine learning, and this will be mostly the focus of the speech of today, but because this is the part where we have achieved more results, and I want to give you some hint of what we have done in these days. And then also, of course, there is the line of interpretable machine learning. I will also try to distinguish what is the current taxonomy, and then human in the loop, achieving this ideal conversation between the machine and the person, the decision maker. And finally, we want to also to observe the decision making from the point of view of the humans. So, which are the mental models of human decision making, and trying to achieve a bridge between cognitive science, psychology scientists, and science, and also machine learning. very shortly, some basics just to set the stage. So machine learning process, it aims to learn, so in the black box, from the training set, we learn a sort of an algorithm, a model, something that when we give a new input is capable of suggesting a decision. So what do we learn from this phase? It's a model that, or an algorithm that can be a decision tree, a set of condition rules or logic rules with some statistical information, but can be other learning models, deep neural network. It's where you have plenty of millions of nodes and links among nodes and millions of parameters to be set. So there are models which are already recognized to be easy to transform in something which is human understandable, decision trees, but also linear models. And there are those which are called the black models. So those which the internal are not easy to be transformed in something which is interpretable by humans. And here is the big game. So okay, before going in the method, going deep in the methods, I want to try to give you what is an explanation. So let's start from the final part of the story. So things that explanation. So what is an explanation? Something which is there since Aristotle was trying to argument on what is a good explanation. Explanation may be a story, a parable, or can be an example, or can be a statistical representation. Can be depending by the background knowledge. There isn't an explanation that fits for all. So, and there are different objectives by those which are looking for explanations. So there are end users. Imagine to an end user to a recommender system. So am I being treated fairly? Can I contest the decision? There's another explanation is also support your right to contest the decision. What could I do differently to get a positive outcome? In this case, it's not an example, but it is a counter example, which is useful also for reasoning for the person. So that might be the engineers. And is my system working as designed? Also the regulator. Is the system compliant with the law? So there is a different at the table. There are different potential users with different background, and all this panorama, it's on the table in the current research of explainable AI. So there are really there is attention to all of these typical different types of users. So an explainer should model the user background. So there are explanations which are statistical flavors that are like features. Explanation as feature properties, relevance properties that try to capture by the in the explanation what has been the contribution to that specific decision or of the different features, how the values of different features contributed to the decisions. So this is the feature relevance. In the same area, for example, saliency maps for images. It's another contribute. So with respect on the input space, what are the features which have more contributed to that decision? In this case, the features, as you know, in image are just the pixels. So the plenty of pixels are, and the values are the color. The three colors of. So so for example, the prediction of Janko Bird. So all those are this picture. You see the different algorithms. How different algorithms which is the saliency map produced by different algorithms, not algorithms like explanator algorithms, but simply it is computed out of the execution of those algorithms. And you see that actually there is different portion of the picture as being highlighted by different algorithms, so to achieve the same prediction. Same feature relevance in the test. So again, it's highlighting portion of the test which have been particularly relevant for that decision. Other kind of explanation with prototypes. So what they do here is essentially they try to highlight which again portion of a picture, of an image in this case, but taking some pieces from the training set, portion of images from some exemplars of the training set, which was very similar to the one of the, it's a simplification, to the one of the case. Explanation as a narrative, a composition of multimodal explanation, images plus text, where as a narrative in natural language you can tell why it was that picture was recognized to be a western crab, and then because it's a large bird and what else. So it's constructing a narrative. Or an explanation as a counterfactual. Counterfactual means that you expose which are the features which have been contributed to a certain decision, and how those features might be, the values of those features, changing the value of those features, you'd have received a different recommendation. So this is the case of a bank credit. So the credit has been declined, rejected, because those features were too high. So the number of so your age, so some of them. So the following features were too low, and then the following features are required to change. So you can see pictorially. So what you might change. Of course, not necessarily all the features can be changed. So your age cannot be changed. Of course, your lung has been declined because you are 50. You cannot change that. So, but from the point of view of the end user, providing an explanation as a counter examples, it's very, very effective. Some psychologists, for example, they say that it's even more effective than providing the factual information, because this activated a sort of what-if analysis, a sort of so what I can change. It's more efficient in terms of cognition process that is capable of activating. Okay, so now I'm trying to give you a sort of taxonomy of which are the methods in this area. So how to open the black box. So what is the scene behind the methods which are behind this? So what are the explanation methods? So there are two big categories. One, it's explanation by design methods. So they say, okay, there are models, as the one I was showing before, the decision tree, for example. So learn models which are explicable by design, natively, intrinsic, or otherwise. The other line, it's called black box explanation methods. So you stay with your black box, you train an efficient black box, but then you also provide an explanator. So you add an extra element. So in the first case, so you try to realize machine learning methods which are very transparent. So you try to increase the transparency of your methods by design natively, or In the second case, you add an extra subsystem, an explanation subsystem, which is capable of providing explanation. So provide the prediction and the explanation as well. Okay. So the by design, they can be, they are of course global and specific of a certain model, like like I'm learning a decision tree. That's the case. The typical example of explainable by design this method. But of course, decision tree, they are very explainable, but when you have an enormous number of features, maybe not very easy to understand as well. So even there my problem. So the black box explanation methods, so post hoc explanators. Again, there is a line of research that can be global. So essentially, you have a black box. You try to reconstruct another global model which is transparent. So it's a sort of which is capable of mimic the black box. Otherwise, there are local explanators. The local explanators are those that you renounce to construct an entire corresponding global model, but simply the explanators works case by case. So once, and then we will see how it works. So that's the global model. So. And then, so explaining globally means replace the black box model capable of replace with like a decision tree, which is globally coherent with the black box, or otherwise you have a local explanation for your explanators works for every single explanation. You provide a prediction, and then for that you are capable of providing, and we'll see example on this. Of course, and again, these post hoc explanations can be model specific. So we can do something which depend by knowing well the logic of the neural network which is behind no, I mean not the logic. I mean the technicality, or the kind of constraints. The property of the constraint, what else, or model agnostic can be an explanators that works for any different model. So the model specific, it's when you construct the explanators depends by the specific architecture of the neural network that you are explaining, or otherwise you can be completely agnostic. So it's independent. It is independent. That means that we will see it audit the black box. It's a sort of a re-engineering process. The black box is there, can be audited as many times as you want. So, and then you observe from the input-output observations, you are capable of reconstructing something which can be transformed in explanation. The types of data are strongly influence the kind of explanators that you can construct: tabular data, image, and text. Those are the three forms of data on which there is plenty of research, and the families strongly differentiate among those kind of, of type of data. Now I will concentrate on local explanation, on first on this providing post hoc explanation, but for a single instance. So it's we observe the input and output, and then what we can do, or we can try to the problem of this auditing problems, like in testing, the problem is how to generate the testing for the audit. So in order to have this observation, I will start from the most famous, the first proposal in this area was done by Lime in 2016 at the KDD 2016. So essentially, what is the idea? So you have a point that has obtained a prediction, and you know everything of this point. So you ask the values of the feature of this point, and you obtain the prediction. Now, what you do starting from this point, the values of the features at this point, you start to generate locally a set of points, and then generating this point, for each of these points that you are generating, this neighborhood, you ask your black box to audit, to give a label. It's you use the black box for labeling your data. Once you have enough data, and that's of course, one of the problems, when you have enough data labeled by your audit, your black box, so some positive and some negative. Now, on this reduced, this is a training set now, which is much smaller than the one you have before. And on this training set, on this small data set, you can train a transparent model. That's the idea. That's the idea. So I first, so I generate a neighborhood. I try to generate a neighborhood capable of recognizing the border of positive and negative class to understand the behavior of the black box, and then so the schema. This is the algorithm, the kind of. I mean, there is plenty of proposal, but we stay online, which is the basic one. But there has been plenty of further extensions. You see, it's so the first part. So you have X, which is the instance to explain some transformation, but don't look to this. Then from this instance, you generate sample around. So generate a neighborhood. Then from this generation, again, this is an interpretation step, which is transformation of data. But then from this neighborhood that you have generated, you go and you audit the black box. You audit the black box. Once you have for all points that you have in your neighborhood, then you generate a regression, which is something that we can an understandable, interpretable model. So so we have also worked on this, and I started with it, and we have improved very much the approach of Lime. We have, and the way the improvement is done, we have done in this direction, but there are plenty of other approaches that from this initial very good idea of Lime, plenty of researchers being activated. So the kind of improvement that we have done is, first of all, this idea using the way we generate the neighborhood is not randomly as Lime do, but it's using a genetic algorithm such that it's which is small perturbation of the initial data to be distributed. And then the second modification that we have done is that in the generation of this, once we have generated this neighborhood, we learn a decision tree, and we learn a decision tree, and we provide the rules, but also we extract counterfactual by this decision tree. So the idea was that to provide not only the fact but also the counterfact that could have a better decision making. So here is an example again. A loan which was be denied, and then so this is the characteristics. Those are the characteristics of the person: age, income, and job. It was denied. So we start with this generative algorithm to which create a very small perturbation on the various characteristics. First crossover, then mutation, till some fitness function it's satisfied, and then so we are capable of generating points: negative, denied, and the circles are the granted one. So the idea is to go around and be capable of reproduce the border. So once we have this neighborhood, now we construct the algorithm, the decision tree. We train a decision tree till it is accurate enough, and then out of the decision tree we are capable of extracting the rule for that specific instance. Why the guy that 20 years old with that income, why it was denied? Because its age was less than 25, job was a clerk, income less than 900. That was the motivation why it was denied. But counterfactual say if its income was greater than 900, in that case it would have been, he or she would have been granted. And also if the age was between 17 and 25 and with another job, he or she would have been granted. So, and of course just to show you the comparison, the kind of improvement that we have done with respect Lyme. The first improvement was this, using this genetic algorithm. In those two pictures, you can see the two. One, it's generating the neighborhood in a random way, as Lyme does. So the star is the point, then randomly you generate points to have enough surrounding. The way with the genetic neighborhood you generate the surrounding is very, very close to the point. So, and then comparing the two algorithms, the explanations, the two explanators on several data sets. So the improvement both in the fidelity and also in the quality of the explanation, it's Laura has been a really a reasonable improvement. Of course, then Laura has to be stable. So that means, where is the critical point for stability? Is that you don't need to generate only one decision tree in the neighborhood. You have to generate plenty of decision tree. So, and then you have to merge plenty of the decision tree. It's still they stabilize, and then you generate out of them a decision tree which generalize of all them. Then the other improvement is that, of course, the counterfactual, they have to be actionable. So you cannot ask people to change the age, or there are things that cannot change it. So while facts are useful for explanation, counterfactual activate the explanation, but they have to be minimal, short. If you provide as counterfactual all the rules at the end, they're not useful. So there is a criteria for minimality, length, and also utility. Okay, and then we compare the explanations on this which have been produced. So observing just the explanation with the one which have been produced by Lyme and the different other methods, just to give you an idea. So in the case of this is the explanation produced. This is AX. Which are like 10 features, and then the prediction is high in the scale. It's a risk in the compass case. It's information about the age, information about previous criminal actions. So 10 features, and the risk was high. The explanation provided by Laura, it's composed. Okay. The motivation was age was less than 25 days before arrest, half day, what else? And then you have also the different set of counterfactual. So if age was 28, more than 28.5, the risk would have been low. If age was, sorry, I don't know, 23, the risk was medium. If sex was female, medium. So those are all possible. If we compare the explanations provided by Lyme, you have this that age 0.02. It's the contribution to the decision. And then you see here, those are essentially the contributions, positive or negative, that the values of that features had for having that decision. So, and then, but I don't want to, but just to give an idea of the kind of expressiveness, the difference also in the expressiveness of the two approaches. Lorenz has also Slime, plenty other being also extended for images test, and also those are the challenge, because those are a little bit difficult. And again, in the case of test, so the explanation, as I was saying before, it's highlighting several keywords which have been particularly effective. So I think that on test, still this idea of having highlighting the keywords is not yet a good useful explanation, but still we are comparing also on this kind of data. But now, once we are capable, now just to focus on what we are doing, another line that we have, once we are capable of generating useful local explanations, we can move from local to global. From that local explanations, try to construct a global explanation. Simply once you can do what you can done for a specific request can be done for all the training set. And if you have the training set, and you can construct plenty of rules, and then for each element of the training set, you construct a decision tree, which is the explanation, and out of this explanation you can merge the plenty of rules that you have obtained with a different criteria of merging. Try to preserve the information, simplifying the rules, simplifying the rules, trying to union concordant rules, difference on discording rules. For example, you can have if you have a rule that says age between 25 and 35, salary between belonging to this set and these other rules, you can merge them in range which contains both 25 and 40, and what else. This is also an interesting line of research. But now there is also another challenge that we are taking. But what about if we follow this idea of creating a neighborhood, learning the transparent model in this neighborhood? What if we transpose this in a simpler space, not in the space of the features of the training set of the original data path? Is there any method for going in a different simplified space? So this is the case for adversarial autoencoder. So we can use this framework for learning simply an identity function that allow us to transform the input data in a compressed, in a latent space, which is a much more reduced data, in a low dimensional representation such that things there might be more simpler, and they capture what is the conditions for which the input data have been transformed, and then we are capable also of going back to the original space. So that's the idea of the autoencoder. So there are two competing networks that essentially they learn how to minimize the error of going from input X to the GOF of X. So, and once we have, so the idea is that let's learn this autoencoder on our training set, and now we can imagine to do the same things that we have done before with the Lore, so but in the latent space. So we can imagine to learn in the neighborhood, which is in the latent space, to learn there a decision tree, and then we are capable of coming back to the original space. So here is the idea. So we have learned this autoencoder, this encoder and decoder machines, and in between two box, encoder and decoder. So we that have been trained on the training set, and then we when we give a single input, we are still in the case of local explanation. Now we give the instance to be explained, and what we do. So the encoder transform in the X in the latent space, and then the generation of the neighborhood happens in this latent space. This is much smarter because in the latent space, the dimensions are reduced, but those reductions enclose some semantics. Why that transformation of data, this compression of data is incorporate the semantics? Why that overall identity as being because the identity is still valid. So the compression captures the semantics. So we compute this neighborhood in the latent space. In the latent space. Now, once we have the neighborhood in the latent space, what we do? The latent, for each element of the neighborhood in the latent space, we transform it in original space, ask the black box to label, and then come back. Now, this label, which has been provided by the black box, now has been we will attach that label to one of the elements of the latent space in this neighborhood. So now we are capable of constructing a decision tree in the latent space. And we have a rule and a counterfactor. Shall we have finished here? No, because this rule and this counterfactor are in the latent space. They talk about the language of the latent space. Now we can go back. We can go back. So now from the latent space, so this part above is simply this box here. Now we give again the rule and the counterfactor, which are generated by this transformation in the latent space, computing on the decision tree in the latent space and obtaining a rule and counterfactor. Now we are capable of coming back to the original space. How we do this? We do, for example, using these rules in the latent space for generating instances, for generating an extent. We go back to the extensional portion of our training set, and we are capable of producing or capturing examples in that extensional space, which is in the original space, and provide examples. And in this case, so we will provide explanation as examples in this neighborhood. And an example here is on the images. On the images, this is the we trained all this framework on the digits data sets, and then here is the result. So now to this, so you give you give 0 and an instance, for example, which is an image, which is this image, and then you are asked to an answer. So the answer, so the you can see on the right side the examples. These are the input, and those are the output. So I give 0, and then I obtain these 3 exemplars. So those are 3 images of my training set, which are according this framework, which are examples of the image that you have given. And then also we can give a counterfactor. Those 2, which are 4 are examples of counterfactor. And even more, you can be why 4 can be explained by this picture here in the colored ones, where the blue and and red, those are saliency map. You can see the red portion are those which, if you remove this part, change the class. If blue, they are particularly significant for the class. Again, you can see for the 9 is this is the picture for the input. Those are the 3 output, the 3 examples of 9 of the training set, and then 4 and 7 are two counter examples. Okay, and this was so this idea of going back in the latent space. So of course we go there for the complex task like explaining images, but we can do there even for other kind of data, where this is a recent work that we have done. It's for time series. It's again the same game. So we go up in the latent space for time series, and we produce a first decision tree for in the latent space. We have our roots and counterfactual on latent space, but then we made also a further steps. We go back from the latent space to examples to the instances, but then for the instance from the exemplars that we have from the instances, exemplars positive and negative, we computed the shapelet, which is a sort of semantic annotation, so which is capable of return the important portion where there is a dramatic change in the time series, and then this transformation now we are capable of building. Now we are back in the original space, but with shapelet, and we can build a decision tree out of the shapelet. I give you an example. So those are this is a time series that I want to explain. It's a bell, and then listens to be explained. So the explanation is that this is a bell because this is the shape of the rule, and the counter example is this kind of shape of time series. And so those are examples, and those are counter examples. And then I can compute also the factor, the rules. So it is a shapelet. So it is a bell because it contains this shapelet and this other shapelet. So the green are those which are contained, and does not contain the number 7, this one. So the rule is that it is a bell because it contains this shapelet and this other shapelet, and not this one. And the counterfactual says that it is not a bell. It is not a bell because it contains this shapelet, the 2, the 7, and does not contains the 1. So those are the motivation. So another extension has been done using on sequence data, which are very, very important for health data. Extension is done for sequence data and also for multi-label classifier. In this case, the peculiarity is that the neighborhood, the similarity function, so the way we generate the neighborhood is using similarity with respect to the domain ontology. So we are starting now to insert in the process some semantic information. such that, so the explanation also which is produced, the decision tree which is produced, it has also contains information about the captured by the medical ontology in this case. Okay, you can find here there are resources which are available, and the feedback are welcome. Let me, I think, go very fast to the conclusion. So there is also a lot of activity on the explanation by design. Let just me remind the work on the capturing exemplars. These are important because Cinzia Rudin, I think it's so the community is divided. There are those which produce explanation, post-hoc explanations, and those which try to produce explanation by design. We are trying to do both. It's nice, there's a paper that says stop to do post-hoc explanation, but try to construct machine learning which is transparent by design. And that's our proposal for producing exemplars. But there is also an interesting line of research which tries to introduce a knowledge graph in the explanation. Very simply is the work of Fred Deleque that is interesting to follow, which is trying to, in the various layers, to add the semantic, augmenting the features using knowledge graph in order to capture in the decision that semantics. Finally, let me conclude with this idea that I was saying, that we want to have the model, the Dr. House model. So decision as a conversation. So human in the loop, it's an important game. Constructing the narrative, it's another important aspect. And of course, mental model of decision making. So the idea is that so the classifiers propose a recommendation and motivate the recommendation. Then the users start to pose questions. For example, which are the training example most similar to the one that you are proposing? And then there is a reaction. Or give me the dissimilar instance. So what happens if you do not consider that feature instead of the others? So, and start some of the answers may be done, answered with the current with the trained model, and these are trained also explanators. Some of the questions might also imply retraining or reinforcement learning. So this feedback means to design the entire human decision making. So that means that the way we design classifier, that might be able to defer decision or ask a second opinion. And here, and the other question is that, but we should have the appropriate mental models of a human decision maker. And here we are working together with psychologists and also setting up some big experiment, controlled experiment that might, like controlled trials with the prediction and explanation. The same way it happens with treatments. So trying to have, and we will ask the help once we are ready, ask the help of the scientific community to spread, ask for participation to this one. Of course, we are moving in interdisciplinary sectors where there are plenty of methods which have been already studied in an area like psychology or cognitive that may be are used. And there's also human interaction. When I'm saying there's how to realize the conversation. Once you have your algorithm has provided the explanations, you need to build a layer, an interactive an interface with the users, depending by the kind of user. So take home message: we do this for empower individuals against undesired effect, to reveal and protect new vulnerability, implement the right of explanation, improve industrial, help people to make better decisions. There are still plenty of open research challenges. Of course, we know that the algorithms, machine learning, they are learning correlation. So what about causality? Learning causality, it's another importance. And there is plenty of initiatives there. So it's will be probably difficult to have the winning one, but I think it's worthwhile. And the fact there are plenty of other scientists working together is that it's continuous learning and sharing of tools. Here it's a tutorial that is going these days in the IIII with we are collaborating too, which does an overview of current research. So let me conclude with that, with my favorite example, which is from Asimov, that I consider almost at the same level that Alan Turing. At least it influenced my adolescence more than Turing. So, and I think that when he wrote this introduction to a second collection of some short stories, the stories were written like 30 years before, 20 years before from him. But he was reflecting by the kind of world that he was imagining of these robots, and they was not thinking to the fact that the robots were really. So of course there might be risk in this. But we have to put all our effort. So we have solved a lot of problem and technology that had risk. So we have been capable of putting wire arrayed electrical cables. We have done keep railings, stairs with railings, a lot of for each useful invention. So we have been capable of putting our energy in safety. This is also the moment for AI. I think explainable AI, it's one contribution to be sure that we are going in a direction that our AI system are useful and it is for humans. So we have to put effort to make them explainable. It's one of the points. Thank you for your attention. I hope I've been probably a bit long. Sorry for not giving time for, giving time for questions. So it's a collaboration among several projects. I think I stop to share. I'm ready for taking questions.
Right. So thank you very much for your talk. It was very inspiring and interesting. So meanwhile, we have collected a few questions from the audience. And so it will be my role to ask these questions. And most of them, as far as I see, are on the reliability, let's say, of the explanation, around explainability. And so there is one, for example, that asks, there is a trade-off between faithfulness and interpretability / complexity of explanations. How do unfaithful explanations affect trust? Can this be avoided?
Unfaithful explanations affect dramatically trust. Unfaithful may be opaque or maybe wrong. So there are two different. So opaque one are those that we want to avoid. So they may affect, as I was saying before, they may strongly affect the opaqueness, maybe strongly affect trustworthiness, because of course can I trust something that I do not understand, so both things can reduce trust, but also inhibit my agency, because I delegate to algorithms. Both things are very dangerous. So there's the fact that being opaque, the fact of being wrong explanation, that's of course critical. So we have to provide a robust explanation. So the current research, it's trying. There is one dimension that is one measures that we observe. So it's the fidelity with respect to the black box. Of course, explanations are trained or considered or are meant to explain what the black box learned from that training. This do not avoid the fact that in that training data set there are bias. Bias is another problem. So it has to be. So we have to consider to have a fair and ethical pipeline of producing an AI system. And in this pipeline of there are several design phases, and we have to check for fairness, for non-discrimination in any phase. So explanations, it's meant to what may do explanations may let emerge the discriminations, but the discrimination is because try to explain how the black box learned, what the black box learned from that from the training set. So in that sense, also explanation may have bias as well if we do not do a correct design of an AI system as well. May help in discovering, but not is not so it depends by the training set as well.
Sure, thank you. So, and another one which is being posted lately, it's are explainable AI system robust in the sense that similar inputs have similar interpretations? So how do these systems behave with respect to adversarial examples?
Yeah, this is exactly one of the point of a comparison among the methods. It's exactly robustness. So, for example, what I can say with Lore, what we have done, we have tried to the neighborhood that we learn depends. So we learn plenty of thousands of decision tree in the neighborhood to create, and also we expose to some attack. But of course, this is a robustness one of the points. So. And it is part of the design. So we have to put in our design also some validation, strong validation.
Okay. Yeah. Thank you. So I guess the time is quite running, so I will go quickly to a couple of other questions, if you don't mind.
Yeah,
and one is, once a system becomes explainable, isn't there the risk that it becomes more vulnerable?
Okay, so here there is this is a very important question. So that's there might be competition between values, for example, privacy and explanations. Of course, we do a lot of effort for providing explanations, but it's not there. There is the risk that we reveal something which may invade the privacy of someone, or maybe even a bit less valuable. I mean, risk of attacks, because we are revealing something. So that's one of the important research questions. At least with the privacy, that's one. There is tension, of course. If you have data that has if you say that a number, you not reveal anything about the other features, when you start to explain the motivation, is the values of the features, you are revealing something. So that's
I was thinking, yeah, probably maybe like thinking about the mortgage, the loan example, right? So I can find a path probably in which I can, let's say, fool the system somehow in a way that I can get the mortgage.
Yeah, also, yeah,
of
course.
Yeah, sure.
Of course.
And then one.
If you can change, for example, if you know that it's critical to, but this is, I mean, but this is also in life. If you know that the motivation why a bank give you once you have learned the fact that the bank check if you have a car or not, you buy a car. I mean, this is not different than in life. Once you know how someone wants prefer a profile instead of the others, you can decide to behave as that profile.
I guess that we are running, well, we actually ran out of time, but still it was very fruitful, and also the discussion was very interesting. So thank you again for joining our series. So I hope, and I'm sure that all the next seminars will be as interesting as this one.
Yep,
so, and sure. I welcome you to join if you eventually have time to join us in the next series. And again, so thank you again, and we can now close the live session. So it will be the video, just for all the listeners, will remain available on YouTube for, let's say, further views and and training. Okay, thank you again.